Welcome, my fellow math enthusiasts, physics entrepreneurs, and people who are forced to be here. Today, I have the exciting job of teaching you about elastic potential energy. Isn't that so exciting? Aren't you so happy? I bet you are. Okay, if I do this, does it sound like, does it change volumes? All right, ready? La 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 la. I moved my microphone. I got a little thing, and I'm wondering if the sound is more directional now. But maybe. If not, oh well. You can just skip ahead and skip that. Although I suppose you've already listened to it once, so you can't get those 3 seconds of your life back. So today, what we're going to be talking about is elastic potential energy. So elastic potential energy comes from anything elastic, right? Um, Technically, the elastic potential energy we're going to talk about today is only because of Hookean or springs that obey Hooke's law. We're going to generalize this to a whole bunch of things that this probably shouldn't be generalized to, but we've already assumed there's no air resistance, and we have what else have we done? We've rounded the acceleration of gravity to 10, and I'm sure I've broken a whole bunch of other laws and been imprecise in other ways, so you're probably fine with it by now. So just so we're clear, technically, this doesn't apply to all rubbery things in the universe, but we're going to pretend it does. All right, so let's talk about energy stored in springs. First off, when I say spring, you've got to understand that. Come on now. Pardon? There we go. All right, you've got to understand that spring means stretchy thing, right? It's not necessarily going to be a coil of metal that has been heat treated to have an elastic property, right? It could be rubber bands, it could be no, not catapults. It could be other rubber bands. I don't know. Anything rubbery and stretchy. Bread dough. Probably not bread dough because it doesn't stretch back. Like once you stretch it, it's stretched, right? But anything you stretch and then it goes back, those things. All right. So the potential energy stored in a spring is equal to the work a spring will do on an object when it's released and returns to its rest length. So let me kind of demonstrate what I mean here. Let's say you've got like a little thing here and you've got a spring, and then this spring is squished, and then you go ahead and you put your text color, pardon me. There we go. Okay. You put your favorite block here. This thing is squished, and then of course you've got your big old fat finger on this thing. What are your finger? I'm not going to try and draw your fingers. They look like that. You've got your finger on here holding it in place. Once you release your finger, whoops, sorry about that. Then this thing is obviously going to get pushed that way, and then your spring will return to its rest length. Okay. Because you've compressed this spring and then put something in front of it, that spring can now apply a force to this as it moves and does work on the object. Ergo, it's the work the spring will do when it is released. Okay? So let's go ahead and talk about the work a spring will do. Work is equal to change in energy, but that's not terribly helpful for us in this situation. We want to know specifically how much work a spring will do based on some properties we know about springs. So we want to look at our force times our displacement. Okay. So the problem with springs is if I have a spring compressed to here compared to a spring compressed to here compared to a spring maybe at its rest length like this, the entire time you are applying a force and squishing your spring in that direction, the farther you push, the more the spring resists. And we know that because of Hooke's law. The force of springs is equal to negative, but whatever, kx. The farther this distance, x here, is, the more force your spring is going to apply. So when your spring is this teal one, it's applying a different amount of force than this pink one, and it's applying a different amount of force than this red one, all because the distance is changing. So when we looked at the force done by gravity, right, the work done by gravity was equal to the force of gravity times distance, but the force of gravity, whether your ball is here, here, or here, is always the same. It's mass times the acceleration due to gravity on whatever planet you're on. It doesn't vary as the object moves. So for us to be able to figure out what is the work done by a thing with a changing force, we're going to have to employ some thinking here, because we can't just plug negative kx in, right? So let's go ahead and look at it. All right. Let's say we have a spring and it's been compressed a length x. Here's x. Okay. What we're going to do is we're going to graph our force of our spring as a function of x. So here's force, here's x. So when it's compressed x, it's going to have some value. Then we let it out a little bit, maybe say to there, it'll go down a little bit. And then we let it out here an equal amount, it will go down an equal amount. And then we let it out some more, and then it will go down some more. And then we let out some more, and you can see that this will continue until it gets to the rest length and equals 0. Because Hooke's law is a linear equation, this force will be linear as we slowly let it out. So we're going to get a graph that looks like this. Let's compare that to our force of gravity. We'll do it in green. When we've got our ball here, the force of gravity is this. When our ball is here, the force of gravity is the same. When the ball is there, the force of gravity is the same, it's constant. So for our work done by gravity, it's the force times the distance. When we multiply this force here times this distance, what we're doing is we're finding the area underneath this green line. So all we need to do is find the area underneath this blue line, and then that will tell us the work done by a spring. So this distance here is just x, right? It's how far the spring was compressed. We need to figure out what is this height here. Well, this height here is going to be how far it was compressed times the spring constant of this spring here. This is k times x. Okay, so the area of a triangle is 1/2 base times height. The base is x. The height is kx. So if we simplify this, the work done by a spring is 1/2 kx squared. Cool. Okay. And that's how we get the work done by a spring, and that's how we get the potential energy of a spring, the elastic potential energy. So, like I mentioned before, a lot of places you will see elastic potential or any potential energy as a U with a subscript. I may stray from that and put E sub E for energy elastic, because I don't necessarily do a great job of differentiating between potential energies and energies. But just be aware. So our equation is 1/2, meaning the number halfway between 0 and 1. K is our spring constant. And X in this case is the compression, or it could be stretch, gotta sound it out, length of our spring. So as long as we know how stiff the spring is and how far we're either stretching it or squishing it, we can figure out how much energy has been stored in the spring and how much work it will do to an object once it's released. Again, the difference between saying it has energy and it does work is just the difference between how we define our system. If we have our spring and a mass, and we say the mass is the system, the spring will do work. If we say that our spring and our mass is all one system, we conserve energy, because a system can't do work on itself. So we're just shuffling around the energy between it being in the spring and it being in the kinetic energy of our box. Whereas here, the box has no energy, then the spring does work on it, and then the box does have energy. All right. Let me take a brief detour, and we're going to talk about a metaphor to help us maybe understand energy. Not that any of you have really complained that, Mr. Barton, this idea of energy is confusing to me, but I think this will help you understand a little bit better. So, let's say you're in a family. Pretend you have a family for a second. Your family consists of your sibling, gravitational potential energy, your guardian, elastic potential energy, and you, the shining golden child of mechanical energy, kinetic energy. Okay. As long as we say that the system is everything of interest in the group, so to speak, then energy is conserved. And the way we're going to think about energy in this case is cash money. So let's say we have an object that's raised up a little bit. That means our sibling, gravitational potential energy, has $1. Okay. Then an interaction happens. The object falls, and the object speeds up. What happens is it's like you have something that your younger sibling wants, say a cool Pokemon card, and you trade it to them. The interaction happens, and they give you the $1. The total amount of money in the system is still constant, right? We didn't change how many dollars there are. We could even say we've got a spring that's way loaded up, right? And then something happens. The spring releases. It sends the thing propelling forward, and it's off a ramp, so it raises up. In a closed system, the spring will relinquish all of its energy and spread it out between the other energies. Okay. There are things in the world, though, that happen to sap energy out of a system, right? So let's say there's something like friction. Okay? And every time something moves, friction takes a little tax out of it, right? So we've got our money in a spring. The spring uncompresses. So it gives a little bit of its energy to the object, making it move. It sends the object flying off a ramp, so it flies up into the air. But friction steals a little bit, and the energy leaves the system. And now the total system has less energy, because anytime money leaves the system, or it could enter the system, then This idea here, anytime it crosses this boundary is work. Okay. So as long as you and your family are exchanging services, right? You give your mom some money for rent. You give your younger brother some money for going out with his friends. And then your brother decides that he actually wants to spend that money on your Charizard instead. All that money stays in the family, and the family, the system, still has the same amount of money. It's only when an outside agent, like the tax man, friction, or maybe it's a benevolent person, and they've got like, like goods and services to hand out, and they give you money as a donation. That could be work done. I don't think that this came out nearly as well as I hoped, but we'll live with it. All right, let's do some examples incorporating elastic potential energy, and then you can go play with it on your homework. All right, so it says you go to the hardware store and with your parents, and they let you buy a spring rated at 200 newtons per meter. When you get home, you put your Pinewood Derby car, and if you've never done those, they're just like little cheap wood cars with like some cheap plastic wheels and stuff. If you take engineering, you probably make one. You put your little toy car in front of the spring, compress it 10 centimeters, and then release it. How fast is your derby car going once it leaves contact with the spring? So here's the situation. Against the wall, you've got your spring, and then you squish it a little bit, and then you put your slick looking, and they all look kind of like this. They're always really ugly and like don't work very well. Anyway, you put your Pinewood Derby car in front of the spring. The spring has been squished 10 centimeters. And we know the mass of our car because there was like a rule when we when we entered the Pinewood Derby competition. It had to be 300 grams or less. And our father said, or mother, I don't know, maybe your mom helps you with your arts and crafts, said, the heavier it is, the more gravity will pull it down the ramp. And then you're like, yes, papa. And then obviously it had to be the max, 600 grams. All right. I don't know if this is just like me as a kid, but anytime we'd go to the hardware store, my dad would take me to Ace, and he'd have to get something, right? He'd be like, I need to get some washers and some ball bearings and a piece of wood, you know? And I'd be like, Dad, what's this thing? And then I'd hold up like some dingle bopper, like just some random piece of hardware that I was like, ooh, Dad, look at this hinge. And then I'd hold like this metal hinge up, and I'd be like, Dad, can we get a hinge? And he's like, what do you need a hinge for, kid? And I'd be like, I don't know. It's just cool. Can I get it? And he'd be like, no, put that back. I'm not made of money, you know? But I always wanted a hinge, and he never bought me one. So this is just wishful thinking. Hopefully your parents, when you go to the hardware store and you're like, Dad, can I get this spring? They let you get the spring. Anyway, sorry. Anyway, I'll talk to my therapist about it later. So anyway, we've got our car, and it's squishing a spring, and the spring is rated at 200 newtons per meter. Okay, we want to know how fast is the car going to go after we let go of it. Right now, you've got your finger on here. I'm not going to draw another hand, but you're holding it so it doesn't go anywhere. How fast does it go? This is a classic energy conservation problem. So for all energy problems, the thing we want to do is say the initial amount of energy, I'm going to modify this a little bit, plus any work done equals the energy at the end, F for final. Okay, so for our system, let's just go ahead and say it's the spring and the car. Okay, so our spring won't do work, it'll have energy. Small distinction, but you know, we should get used to it. Okay. It doesn't say anything about friction, and let's say we've got some nice wheels, so there's no friction. We don't have to worry about that. So at the beginning of our problem, the energy we have initially We're not moving, so there's no kinetic energy. We're not going up and down, so there's no gravitational potential. But there is a spring being squished, so we would say we have some elastic energy initially. Because the spring has energy, it cannot do work. So there's no work from the spring. There's no friction sapping energy from our system. There's no rocket booster. There's none of that. So there is no work done on our system. The total amount of energy is constant. It's conserved. This equals our final amount of energy. So at the end, our spring will have extended itself, and then our car will get some speed lines on it because it'll be going somewhere. So the spring has returned, it should be a little longer. It's returned to its resting length. Because it's at its happy place, there's no energy stored in it. If I put something next to it, the spring won't extend farther. It's at its happy spot. It's stuck there. There's no energy in the spring. So we have no elastic energy. I don't see any ramps, so we're not going up or down. There's no gravitational energy, but the car is moving. So we have energy kinetic as our final energy. Now we just plug in some equations. Energy elastic is 1/2 kx squared. Energy kinetic is 1/2 mass times velocity squared. All right, we can multiply both sides by 2 and cancel the 1/2 so we don't have to worry about that. Then let's plug in some numbers. K is 200 newtons per meter. Because this is in newtons per meter, we should have everything else in meters also. So 10 centimeters, this is 0.1 meters. So we're going to have 0.1 squared equals mass. Newtons. A newton is equal to a kilogram meter squared per second squared. Because this has an invisible kilogram in it, this should be in kilograms. So that would be 0.6 kilograms. So 0.6. And then velocity is what we're looking for. Because we've converted everything to meters and kilograms and seconds, this will come out in meters per second. Now we're done with physics. Now we're just doing some algebra. So 0.1 squared is 0.01, which is the same thing as dividing by 100. So 200 divided by 100 is 2, equals 0.6 v squared. We divide both sides by 0.6. And then we grab our calculator. 2 divided by 0.6 is 3.3 repeating forever. It's 3 1/3. But, bar there. V squared. Now we take a square root of our answer. Whoops. Square root of our answer. And our velocity is about 83, if we round correctly, 1.83 meters per second. That's exciting. How fast is that? That's like maybe 4 miles an hour. So not super fast, but fast enough that it's cool, right? If you think your dad letting you buy a spring at the store is cool, then it going 5 miles an hour is cool too. All right. Very simple problem. Elastic energy converts into kinetic energy. Pretty straightforward. Let's look at another problem that's maybe it's probably just about as equally straightforward. And then we'll look at 2 more problems, maybe one long problem. So it says, there is a spring at one end of a smooth table. Smooth here kind of implies that there's no friction, with a spring constant of 100 newtons per meter. You slide a mass of 0.5 kilograms at the spring at 4 meters per second. So we've got our mass. This thing is 0.5 kilograms, and it's sliding with a velocity of 4 meters per second. We don't need to worry about it slowing down because it's a smooth table. How far does the spring compress when the mass comes to a complete stop? So it's going to run into our spring. And because there's this heavy thing squishing, it's going to make our spring compress. And then we'll have our mass like this. That doesn't mean the system is stable, right? Of course, our spring, if we don't put anything there to stop it because there's no friction, the spring is then going to uncompress and then fling the mass back that way. How fast do you think it's going to be going when it does that? You don't know? We'll look at it. So let's go ahead and solve this problem first. When this thing runs into it, it squishes the spring. What is the maximum squish we get? Actually, that shouldn't be there. That should be more like here, right? How far is this distance right here? From where it was to where it is. So, initially, we have some kinetic energy because the object is moving and it's got some speed. So, our energy initial is kinetic energy. Okay. Plus any work done. Do we have anything doing work here? Not really. There's no friction, there's no rocket boosters, there's no parachutes, there's no dog. So no work is done. Equals energy final. So our final energy, when it gets here, it comes to a complete stop. So velocity, V final, is 0. That tells us that there's no kinetic energy. Where did all that energy go? Well, if we're saying our system is the spring and the mass, it's been transferred into elastic potential energy, and it's been stored in our spring. So now we just fill in our equations. 1/2 mv squared equals 1/2 kx squared. The 1/2's cancel because we can multiply both sides by 2. And now we're just plugging in numbers. And we're doing some algebra. So our mass is 0.5. Our velocity was 4. And 4 squared is going to be 16. Equals K is 100 newtons per meter times our squish squared. Our compression distance squared. So half of 16 is 8 equals 100 x squared. We divide by 100, 0.08 equals x squared. And then we take a square root of 0.08 to get x. So we do 0.08 square root of that. And we get about 0.28. So this is 0.28 meters because this is in meters per second and newtons per meter. So our answer comes out in meters. This is about 28 centimeters. I think that's a little over 10 inches for those of you who like the less popular American measuring system. But there we go. We could answer that question. How fast is this going to go when it rebounds? When the spring goes, okay, you squished me, now I'm going to unsquish, and pops it back off. So it'll extend back out, and then our box will be sliding that way. So we're going to have, at the beginning, some potential energy, and then it turns into kinetic energy. This is just the same problem in reverse. So we get the same amount of energy back out. So it's pretty easy to see that you're going to be going 4 meters per second, right? Interesting. All right. You're saying lame, not interesting, Barton. This is just a block sliding on a fake surface. What's perfectly smooth? Nothing. This is unrealistic. Teach me real physics, Mr. Barton. All right, we'll do a real physics problem. Real physics. So you and two friends are at a skate park and you've brought your water balloon launcher, which is essentially just a giant rubber band. It's like surgical tubing with some handles on it and a little basket for your water balloon. You're trying to figure out the spring constant of the water balloon launcher, obviously. So one of your friends is at the top of a 2-meter tall vert ramp and drops in. So, all right, let's start drawing this. So we've got our vert ramp like that. And then your friend, what do skateboards look like? This is going to get really ugly really fast. Your friend is standing up here. Helmet on, of course. And then they've got their skateboard. Like that. Anyway, some wheels. And they're about to drop in. You and your other friend are sitting here holding. What do you and your other friend look like? Holding the water balloon launcher across their path. Like this. So this person's going to drop in, slide into the water balloon launcher, and somehow this is going to tell us K, we hope. I think. I haven't read the whole problem yet. The other two hold the water balloon launcher directly in the path of the person on the ramp. The person on the ramp with their skateboard has a mass of 70 kilograms. And when they roll down the ramp, they get caught by the water balloon launcher, and they're going to stretch this thing 1.3 meters. Maybe you have your fourth friend like mark the initial length and the final length with some chalk or something. You take out measuring tape. What is the spring constant of the water balloon launcher? Okay, so this problem is a little more realistic and a little more complicated. So let's start it like we should every single energy problem. And we're going to say the energy initial plus any work done equals the energy final. Okay, energy initial. This person isn't moving and this rubber thingy isn't stretched yet. So what kind of energy do they have? Well, this distance here is 2 meters. So we have a mass that has been raised from h equals 0 to h equals 2. We have some gravitational potential energy because this person can fall. So our initial energy is going to be energy gravitational. There is probably some friction involved here. However, you have your like really rich friend do this with their really nice skateboard with those Black Panther bearings that you like. You know when you stick your skateboard up and you kick one wheel and it goes whoosh, and just spins forever? It's those bearings. They're super nice. So we're going to say no friction or anything. There is, but negligible. They've got nice bearings, you know? So that's this side of the system, right? Now, let's think about this. Final. This person's going to drop in, and then at some point, they're going to be here, right? And they're going to be skating towards you. They have kinetic energy. But this is not the point we're interested in. Yes, we could say this is the final, and there's kinetic energy of this person, and we can figure out how fast they're going. However, that's kind of an intermittent step. It's in the middle, and it doesn't ask us how fast they're going. We could find it if we really cared, but we don't. What we want to know is the spring constant. So let's skip this part and go to the part where they are in the rubber band. They've stretched it as far as it will go, and then they've stopped before the rubber band slings them back towards the ramp. Okay, so we're skipping the middle here, even though we could find the speed if we felt like it. And we're going straight to the end where the stretchy thing is stretched. What kind of energy is stretchy energy? Elastic. So our final energy is elastic, and there is no kinetic energy because they slide into it and it stops them. And then we record the maximum stretch before they get slung back. All right, now we're just doing algebra again. Energy gravitational is mgh. Energy elastic is 1/2 kx squared. And now we are plugging in numbers and we're doing algebra. You're done with the physics. The physics is drawing the picture, telling yourself a cool story, and writing 3 lines of really simple equations. Now we're doing algebra and we're plugging in numbers. So the mass of this beloved friend is 70 kilograms. G on Earth is 10. We don't necessarily care about the negative here because it's energy, right? Like, I don't care if energy can't be up or down. It's a scalar. The only thing we would really care is if they're going opposite the direction of gravity, but they're not. Gravity's pulling them down. They're going down. It should be positive. The height of this ramp is 2 meters. So 700, or 7 times 10 is 700 times 2. It's 1,400 equals 1/2. K is what we're looking for. The distance our thing stretches, our water balloon launcher, is 1.3. Whoops, not 0.13. It's 1.3 squared. 1.3 squared is equal to 1.69. We can multiply both sides by 2. Let me just double check that that's true. I don't want to lie to you and have squared something wrong. That would be embarrassing. It is, in fact, 1.69. Multiply both sides by 2 to move the 1/2 over. So this is 2,800 equals K times 1.69. And then we do 2,800 divided by 1.69. And we get K is equal to 1,656.8 newtons per meter. Perfect. We now know how stiff or stretchy our rubber, our water balloon launcher is. Sorry, I touched the ADD there. I was losing track of my thoughts. All right, so we have K. Wonderful. What a fun problem. And you're thinking to yourself, Mr. Barton, that was indeed not a fun problem. That was a lame problem. Show me a cool problem. Here's a cool problem. Here's why you were so adamant about finding K. Using the constant you found from the previous problem, so let's write that down before I forget. K, lowercase k, equals 1,600, and was it 58.6? 56.8. 56.8 newtons per meter. Using the constant you found from the previous problem, find out how high a 2 kilogram bowling ball can be launched by loading it into the water balloon launcher, stretching it 1.5 meters, and then sending the ball up the vert ramp. So now we're doing the inverse. We have our vert ramp. We have our launcher. And we put a bowling ball in that thing. Please don't do this. And if you do this, I didn't tell you about it. So you're going to stretch this thing so that from resting to here is 1.5 meters. You're going to load a bowling ball, and then you're going to fling that thing to the vert ramp and watch it go soaring into the sky. This will probably destroy your vert ramp and or your bowling ball. So be careful. Also, you're flinging a 2 kilogram object into the air. You could kill someone. Please don't do this. Assume the ball travels straight up. So when it leaves, it goes perfectly vertical and whatnot. Okay, so what kind of energy does our bowling ball ramp spring system have at the beginning? At the beginning of the problem, our bowling ball ramp spring system has elastic energy because we have a thing being stretched. So we have energy elastic. Perfect. No work. I'm sure there's friction between the bowling ball and the ground and all kinds of stuff, but c'est la vie. You know what I mean? It's not our problem. This is intro to physics. This is physics 101. This is high school physics. Everything's a sphere. Friction doesn't exist. There's no air resistance. You know, we'll carry on with our lives. So, no work done equals final. Okay. We could, and this might be fun, figure out how fast our bowling ball is going as it enters the vert ramp. But the problem is asking, how far up does it go? So we're looking for the maximum height. The maximum height will occur after this thing. It goes up, slows down, stops, and then starts to fall back down. So because it's not moving, the spring is no longer stretched, and it's just a mass that can fall. The only type of energy we have is gravitational. Now we're plugging in some numbers. We're doing algebra. Elastic energy is 1/2 kx squared equals gravitational energy is mgh. All right. 1/2 times k is 1656.8. X is the distance of stretch. This is 1.5 squared. Equals the mass of our bowling ball is 2. G is 10. And we're looking for H. So now we do some simplifying. So let's just multiply this whole side out. So we have 1/2 times 1656.8 times 2.25. And we get 800, I can't read, 0.9. And what is the units of this? This would be in joules because it's measuring energy. Equals 20 H. Divide by 20. Divide by 20. Divide by 20. And we get the height of our bowling ball. It's going to go 93.2 meters into the air. That's almost... Actually, that might be the length of a football field, since football fields are in yards and meters are slightly longer than yards. That's pretty stinking close to a football field high. Yeah, please be careful. I'd like to reiterate that you didn't get this idea from me. I told you specifically, hypothetically, if you did hear about it from me, not to do it. And third, wear helmets. I don't know. You're shooting 4 pounds of bowling ball almost 300 feet into the air. You're gonna hurt somebody. Don't do this. I'm just gonna end the video before you get any funny ideas. I'll see you guys next time.